We can start. We can start.
Okay.
Okay, so well, welcome Stephan Baier, who will tell us about small solutions of generate ternary quadratic congruences. Thank you, Stephan.
Yeah, thank you. So in the last week we have heard a lot about representations by quadratic forms. In particular, Vinay covered representations by quadratic forms. One can consider the problem also in Z quotient QZ, in the ring Z quotient QZ, in which it is also very interesting. So in this case, one asked about congruences, quadratic congruences, rather than quadratic representations. Yeah, the situation is the following, that Q, x1, x2, x3 be a ternary quadratic form. We are interested in the distribution of solutions of a congruence of the form Q, x1, x2, x3, congruent 0 mod Q. Of course, one can also consider the inhomogeneous case, which is more difficult. What we are particularly interested in are small solutions, so the existence and the distribution of small solutions of such a congruence. There is interesting work of Heath Brown about this problem. So a part of this talk, or this work, is inspired by Heath Brown's results. Yeah, the ternary case is particularly interesting. The more variable one has, the more freedom, and the less difficult the problem is. Okay, yeah, we want to assume the modulus to be odd throughout this talk to avoid certain troubles. Huh? No, can be any odd number. So actually we consider two cases when we have prime powers and square-free numbers. Okay, but let's come to that later. Yeah, let's call the maximum of the moduli, the absolute values of x1, x2, x3, the height of the solution. Yeah, so then our main task is to find a solution of height less or equal q to the theta, whenever q is large enough and theta is a fixed number. So we would like to find out for which theta can we prove the existence of a non-trivial solution of height less or equal q to the theta, if q is large enough. Non-trivial means not equal to 0, 0, 0, which always satisfies the congruence. Yeah, more precisely, we are interested in an asymptotic formula for the number of solutions, which is a more difficult problem. And we consider two situations. One situation is when we fix the coefficients from the beginning and let q vary, let q tend to infinity. The more interesting situation is when we allow also the coefficients of the quadratic form to vary with the modulus. So that means we take any modulus and the coefficients can be anything of the quadratic form. Okay. In fact, I talked about this problem here already at an earlier conference. So in the meantime, there has been a bit of progress. I formulated a lot of problems in this direction. Okay, so let's see what are limitations to this exponent theta. First of all, there's an obvious limitation. Let's take just, let's take just this quadratic form, coefficient 1. Then we see there cannot be any non-trivial solution of height less or equal square root q divided by 3, because the sum, otherwise the sum of these three terms is less than q. So therefore, this becomes an equation, x1 square plus x2 square plus x3 square is equal to 0, which has only the trivial solution. So this example shows that we need to assume that theta is greater or equal 1/2. If we don't make any assumptions on the coefficients, extra assumptions on the coefficients. Yeah. In fact, Heath-Brown showed when we don't make any assumptions on the coefficients, not even 1/2 is sufficient. So he gives an example of a quadratic form. A, B are chosen independent of Q, such that this quadratic form is such that there is only a non-trivial solution of height greater or equal Q to the 2/3. However, in this example, the A and B are chosen in such a way that the determinant of the matrix underlying the quadratic form is not co-prime to Q. In other words, Q is singular modulo Q. In contrast, this above quadratic form is singular modulo Q. Okay, so therefore, it makes sense to focus on this non-singular case when the determinant is co-prime to Q. Okay. It's reasonable to formulate a conjecture like that whenever we have a quadratic form, ternary quadratic form, which is non-singular modulo Q. There should exist a non-trivial solution of height less or equal Q to the theta for every given theta greater than 1/2. Okay. When the coefficients are fixed, so the situation 1, which I mentioned, then it's not difficult to show that actually there exists a non-trivial solution of height less or equal Q to the theta with theta greater than 1/2. So as I said, the interesting case is when we allow also the coefficients of the form to vary. Okay, good. So then one result about an asymptotic formula from work with Arnold Halder, a PhD student of mine. So we looked at diagonal quadratic forms and the case of prime power moduli. In that case, we showed an asymptotic formula to halt whenever theta is greater than 1/2. Oh. However, what is important is that we make some condition on the variables, namely that the variables are co-prime to the modulus. So the relevance of this condition I will explain in a minute. Yeah, this is particularly for the case of prime powers when Q is a power of a fixed prime. And so to ensure the existence of such solutions, we also need to assume that the prime is greater 5. Okay, so let's see. Yeah, so that's an interesting result which inspired the work on this problem, or at least partly. Heath-Brown showed for the kind of opposite case when the modulus is square-free, the existence of a non-trivial solution of height Q to the theta whenever theta is greater than 5/8. So it's difficult to actually achieve this conjecture, theta greater than 1/2. So he proved greater than 5/8. Then we have a non-trivial solution. So that's a very interesting paper. Good, I will also come to that later on. So for the prime power case, we showed a similar result, namely the existence of a solution of height Q to the theta with theta greater than 11/18. But with this extra coprimality condition. Okay. So note that 11/18 is a little smaller than 5/8. So you see here the numbers. However, one needs to say that it's only for the diagonal case when we have a diagonal quadratic form, and also we focus on prime powers. The restriction to prime powers should not be essential, so it should be possible to do that for all modular Q. But what is essential in our method is that it is a diagonal form. And we can conveniently separate variables in a certain way. But I will not go into that method. But yeah, so that is a challenge, seems to be quite difficult to generalize that method to arbitrary forms, non-diagonal forms. If we could do that, then we could beat Heath-Brown's result. Okay. All right, so next one. Yeah, so why is this coprimality condition important in the case of prime powers? Heath-Brown focused on square-free moduli and explained why this is actually satisfactory. Namely, when we have a non-trivial solution of height q to the theta, with theta greater 1/2, for any large enough square-free modulus, then we can get the same for arbitrary moduli by a simple argument, which goes as follows. So write q as q0 times the square, q1 square, where q0 is square-free. Then look at the solution of the congruence modulo q0. So this now trivially extends to a solution q1, x1 q1, x2 q2 q1, x3 q1 to the congruence with modulus q. Yeah, so you just multiply the whole congruence with q1 square. So if you look at the size of this solution, it will also turn out to be less than q to the theta. Yeah, so when you just assume the solution to be non-trivial, that means not equal to 0, 0, 0, then easily from the case of square-free moduli, you can go to the case of arbitrary moduli. So in particular, yeah, so that's the reason why we actually make this assumption. The variables to be co-prime to the modulus. So in particular, when you look at prime powers, as we did, let's take q equals p to the n, where n is odd. Then you can write, assume also that x1, x2, x3 is a solution modulo p. Then this is a solution modulo p to the n of the congruence. So, and you see, whenever k is large enough, this solution will have height less than q to the theta for every given theta greater than 1/2. So the problem becomes uninteresting if you just assume the solution to be non-trivial. You need to make a coprimality condition, but then it becomes interesting, the problem. So we assume coprimality with q. So then you cannot use that argument in particular. Okay. All right. Yeah, so some remarks on the methods which were used by Heath-Brown and by us. So Heath-Brown used multiplicative characters to detect solutions of these congruences, and in addition, ideas from the geometry of numbers. So it's really quite involved. This paper is not easy to do that. And one key result in his work is a Burgess-like bound for short character sums with binary quadratic forms. I will come to that later, the precise result, because it also appears in our work, which I will describe. In contrast, for this prime power modulus case, we used additive characters. Yeah, so the start is an application of two-Poisson summation, which transforms the problem into a problem about a dual quadratic form with a smaller range of the variables. So when it was n before, then the dual range will be q divided by n, modulus divided by n. Yeah, so then it turns out that so one can isolate the main term easily, that is just the zero frequency, and then you just need an upper bound for the dual count to get a bound for the error term. Yeah, so and that is actually the interesting part. That's not trivial. So we use some ideas from Diophant approximation for that, some results. Good, I will not go into that method. So that's the interesting part of this work. And in particular, the Diophant properties of the ratios of the coefficients with the modulus come into play. So they will be important, as we will see later on. All right. Good, so the question, the point of this talk is actually the question if this exponent 1/2 is a fundamental barrier or not. So can we break that somehow? So we have seen limitations to the size of the least solution, which show that in general we cannot take the exponent less than 1/2. But nevertheless, this does not need to be the end of the story. And in fact, in the recent work with my PhD student Aishik, we showed that, in a sense, for generic forms or randomly picked forms, we may go below this exponent 1/2. So that's actually an interesting result, because both the method of Heath-Brown and our method stop at 1/2. So we cannot get better than 1/2 just using these methods. Okay. And from that, of course, naturally the question arises if we can somehow refine our conjecture about the size of the smallest solution. That means if we use extra information about the coefficients, Diophant information in particular, can we formulate a refined conjecture about the size of the smallest solution of this congruence? Okay, yeah, we got the following result. So in that case, we assumed, yeah, we also took diagonal quadratic forms. We just looked at a family of diagonal quadratic forms, where alpha 1 and alpha 2 are fixed, and we vary the alpha 3. So we consider that family. Alpha 1, alpha 2, alpha 3 are co-prime to the modulus, Q. And in that case, we just make one coprimality condition, namely x3 is co-prime to Q, x1, x2 are allowed to be anything, modulo Q. So that's important for the asymptotic formula, in fact. Yeah, so then what we showed is for almost all of these alpha 3, we get a solution of height less q to the 11 over 24 plus epsilon, which is smaller than 1/2. So we are able to break the 1/2 barrier in an average sense. Yeah, one could make this a little o of phi of q more precise. So yeah, o of phi of q to the 1 minus delta. But okay, so then also this exponent will change. So to keep it simple, I just say we take, yeah, I'm just satisfied with that result because it's already an almost all result. Yeah, so that 11 over 24 is slightly less than 1/2. And we even get an asymptotic formula for almost all of these quadratic congruences here. Yeah, so in that case, when we choose our coprimality conditions like that, just assuming x3 to be coprime to q, then the main term depends only on that alpha 2 and alpha 1. So we also set for this result alpha 1 equal to 1. If alpha 1 is not equal to 1, we can just scale the congruence by dividing by alpha 1. So we assume alpha 1 to be 1, alpha 2 a fixed coefficient, coprime to q, and alpha 3 varies over the numbers which are coprime to q. Okay, in that case we get this main term which just depends on alpha 2. And yeah, we can improve that result under the Lindelof hypothesis for Dirichlet functions from 11 over 24 to 1 divided by 3. So that's the, yeah, 1 divided by 3 is precisely the limit where that becomes 1, basically. So when you have n equals q to the 1/3, then this main term becomes 1. So that is the ultimate limit. Good. Yeah, also one interesting thing, when we just focus on prime power moduli, so we fix some prime p, let's say, and let n tend to infinity, then we can improve this 11 over 24 slightly. We managed 11 over 25 using the theory of periodic exponent pairs as developed by Mallesham. Okay, so a brief description of the method. It's actually, this method is quite straightforward. It's not very difficult. Good, so that is the quantity which we want to get an asymptotic formula for. Yeah. Good, so we use multiplicative characters to detect the congruence condition. Yeah, in that case, since we just assume x3 to be coprime to q, that can be done in this easy way without caring about removing coprimality conditions in that case. Okay, so the main term is simply coming from the principal character. It's that. Can be easily, I mean, it's not a difficult part to evaluate that. The error term is this. Okay. And then what we consider is the variance. So we subtract the main term from this quantity. The main term is just a constant because it depends on alpha 2 just. Okay, we consider the variance. And we need to show for proving our almost all result that we get an estimate for the variance better than that here. Because if you have, yeah, the main term is of size n to the 3 divided by q. So if you calculate sum over alpha 3 of n to the 3 divided by q squared, you get precisely that here. Okay, so it needs to be better than that here. Okay. Good, so when you look at the error term, you see here there are two cases. You can pull out chi bar minus alpha 3, and you get, you need to consider chi bar of x to the 3, x3 square. So that becomes chi bar square x3. So there are two cases when x bar square is the principal character and when it's a non-principal character. So we need to divide our sum according to whether chi bar square is the principal character or not. Okay. So for general moduli, the contribution of the chi bars whose squares are the principal character is that here. Here you have a Legendre symbol or Jacobi symbol. And yeah, that is the second sum, chi bar or chi square is not a principal character. Okay. So then you need to do some calculations. Yeah, so important is what are we using for these estimates? Here it's natural to use Burgess bound. So then we get rid of this factor, and then we are just left with that sum, which we can multiply out, and we can easily count, so that leads to a counting problem after applying orthogonality relations for characters. And that counting problem is not difficult. Okay, here we use Burgess bound, and here we have this sum inside, for which we use exactly Heath-Brown's result. Namely, bounding character sums, short character sums, with quadratic forms, binary quadratic forms. So this appears here. So a character of a binary quadratic form, where the variables run over short intervals. Very interesting stuff. Okay, Burgess bound, I just remind you to Burgess bound for short character sums. That's actually where our 11/24 comes from, not the Heath-Brown result, but we need a non-trivial bound for these character sums of binary quadratic forms. Okay, so that's Heath-Brown's result. In the end, it also uses an argument like Burgess, so reducing the problem to a sum where you can use the Riemann hypothesis. Yeah, but it's quite complicated, in fact. So it's not an easy thing. So this has been generalized actually by Lillian Pierce to more general quadratic, more general forms, forms of higher degree. Okay, so you have a convex set contained in a disk of radius r. So in our case, we just take a square of the same size. Q odd should be square free. And let chi a primitive character, modulo Q. So then when we have a binary quadratic form with determinant Q co-prime to Q, the non-singular case, we get a bound of this form here, depending on R and Q. So it looks like, I mean, yeah, you can guess that in the end, one uses similar arguments as in Burgess bound. Okay, so and that works for a certain range. Yeah, so that's precisely what we need for our result. Good. Yeah, so I will not go further into our calculations. But a bit more calculations one needs to do. But so these are the important results used in that work. So now this result suggests that we may want to try to refine our conjecture about the least solution of a quadratic congruence. So what was actually the constraint? We need to analyze what are the constraints to get smaller solutions in the general case than q to the 1/2. Okay, let's look again at this example, which gave that q to the 1/2 constraint, which is when we have just coefficient 1 here. In general, if alpha 1, alpha 2, alpha 3 are fixed non-zero integers, having the same size, same sign, then yeah, if q is large enough, you will not find a non-trivial solution of height less q to the 1/2 minus epsilon. So you can directly generalize this argument. Yeah, also interesting is when you have not the same sign, so indefinite forms, like Pythagorean triples, x1 square plus x2 square minus x3 square. Then it turns out at q to the 1/2, the behavior of the asymptotic changes. You still get many solutions of height less than q to the 1/2, but they follow a different asymptotic. So our asymptotic breaks down at that point. But so can we formulate more general conditions on the coefficients under which we cannot get very small solutions, much smaller than q to the 1/2. And it turns out, yes, we can. That's the case when these ratios, alpha I divided by q, can be approximated closely enough by rational numbers with a small denominator, simultaneously by AI divided by R, with a small r. Okay, I show you the argument. Okay, so suppose R is such that R times alpha I divided by q, distance to the next integer is equal to beta I. So that we have that. Okay, there's a little mistake here. So in the case when beta I is, yeah, so it may be plus or minus beta I. Okay, but doesn't matter for the argument. Good, then multiply the whole congruence with R, so we get that. We can conclude that here. Okay, we can spell out R alpha 1, so that will be, R alpha I will be AI times Q plus beta IQ, so we'll get this congruence here. And then we can just reduce modulo Q, so this doesn't matter here. We just get this congruence. And now, again, we get a constraint if beta I times Q is small compared to Q. Precisely, when we have the maximum of the absolute values of the beta i's is less than 1 divided by 3 n square, then this congruence turns again into an equation. So because the size of the left-hand side can never be larger than Q. Okay. So then again, this does not have any non-trivial solution because we get an equation. Okay, and we can, so we can formulate it like that. To expect the existence of a non-trivial solution for a large enough Q, the least we should demand is that the size of the maximum of these coefficients is a little bit larger than 1 divided by n square. You can transform that into an inequality for n. Then you get this constraint here, or this condition. And now our conjecture is that, in fact, that's the only constraint, the only obstacle for small solutions. So this possibility that the coefficients may be well approximated by simultaneously by fractions with a small denominator. Okay, so we conjecture that the validity of this condition for all R, together with this condition n greater or equal to 1/3 plus epsilon, from the conditional part of our theorem, should be enough to ensure the existence of a solution, satisfying, xi q is a coprime for some I. Okay. So precisely the conjecture is as follows. We don't want to formulate it as a, we just talk about existence, not about asymptotic formula. Okay, so let Q be odd, alpha 1, alpha 2, alpha 3 integers, coprime to Q. Then this congruence has a solution satisfying xi q coprime for some I of this height here. So in the case when you have alpha 1, alpha 2, alpha 3 equal to 1, for example, then you will find that this is precisely of size q to the 1/2 here. So we recover that case in particular. So that's what this conjecture tells us. It should be of size q to the 1/3 plus epsilon, unless these quotients have a very good simultaneous approximation by fractions with a small denominator. Yeah, so we could also formulate that for non-diagonal quadratic forms, but I want to be a bit careful here. Okay, in that case, we should take eigenvalues of the corresponding matrix, the matrix corresponding to the quadratic forms, instead of the coefficients alpha I. But okay, so something happens when we diagonalize, so also the height conditions change, so that's precisely the point why it's difficult to generalize from diagonal forms to arbitrary quadratic forms. Okay. Yeah, so then I want to formulate a concrete problem. Yeah, is it possible to find a concrete class of quadratic congruences, but an interesting class, for which we can break this exponent 1/2? So when we have certain conditions, if possible, Diophantine properties of these coefficients, can we then predict the existence of a solution with height much less than q to the 1/2? So here we have talked only about an average result, so almost all result. We would like to find a concrete class for which we can show that. Okay, so I still have, how much time I still have?
10 minutes.
10 minutes. Okay, so yeah, one moment. So that's this problem. Yeah, actually, before this conference, I thought about if I should talk about another problem related to this circle of problems, because it would fit with the workshop very well as well. So let me use these last 10 minutes to also talk about some results about inhomogeneous congruences, which is much more difficult. As usual, the inhomogeneous case is more difficult. So that's now disconnected with that. But since I have the time, I will just advertise this result. So, yeah. So, question is, what can be said about small solutions of congruences q x1 up to xn, quadratic form, congruent lambda mod q. Lambda not equal to 0. So in fact, the opposite case would be lambda co-prime to q. So let's assume lambda co-prime to q. So here one needs more variables to get something of the same strength as before. So joined with Anupalda and Akaprava Bandari. So two PhD students of mine. We looked at, so once again, diagonal quadratic forms, but in that case, it should not be the big constraint. I mean, it's just easier for diagonal forms. Okay, diagonal. Yeah, so here we need n greater or equal 6 variables. And fixed coefficients, so we also fix the coefficient and then go up with q to infinity. And fixed coefficients. And established an asymptotic formula. for the number of solutions. Yeah, less or equal q to the 1/2 plus epsilon. So that is precisely, that's always the goal, to reach the exponent 1/2. Yeah, so we managed to do that when we have 6 variables. And the interesting thing is when you analyze the number of solutions, so you start again by detecting the congruence using additive characters, Poisson summation. So what happens then is quite interesting. So first, of course, there will be Gauss sums coming up, quadratic Gauss sums. Then you evaluate them. Then you encounter Klostermann sums and Sallier sums. Yeah, okay, and very important, Q is a prime power. So in the prime power case, you can evaluate the Klostermann sums. And then, in the end, you are led to sums of the following form. So again, the main term pops out in a natural way. It's a 0 frequency. And for the error term, you then are led to sums of that form, less than k, less or equal p. K, okay, let's call it k. Kp coprime, tau n k, cosine 2 pi square root k divided by, yeah, the modulus q, essentially. Or divisors of the modulus, so p to the s. So this is just, if it exists, this is one of the 2 square roots of k lambda, modulo p to the s. Lambda is a certain quantity, so modular square roots. So this doesn't depend on which square root we take, of course, because it's an even function. Yeah, we encounter such sums where, and now this connects to the circle method, tau n k equal to number of representations of k by a dual quadratic form. So we get the dual quadratic form q tilde x1 up to xn. Yeah, and this was explained by Vinay last week. So here we can write this as a singular integral times a singular series. And the nice thing about the singular series is that it decays very quickly when the number of variables is large. And then, okay, so we will get something like that. Can I write here? Okay, I write there. Oh, yeah, okay, I still have the time. Tau n k is equal to, singular times k to some power, n minus 2 or something, n minus 2, right? Yeah, okay, I think, so let me see. Yeah, n minus 2. Okay, so then this part you can remove using partial summation. Okay, that is k here. So actually here also this depends on k. Remove using partial summation in the end. And this singular series is a sum of that form, q equals 1 to infinity, a q k. Okay, and this depends just on the residue class of k modulo q here. So for that reason, we can write our expression in that form on that side. Okay, let me just do that. But I will finish in a minute. So we pull out a Q summation. Q equals 1 to infinity. Yeah. L mod Q, L co-prime to Q, L co-prime to P. Huh? Okay, yes. E QL. Okay, so we need to take modulo PQ and then divide by P. I think. Okay, something like that. So, and then K, congruent L mod Q, 0 less than K, so equal capital K. This goes and okay, so this decays very quickly with respect to Q, so therefore it works like that. And so therefore just small Q's matter when we want a bound, upper bound. So therefore this congruence is not much of a problem here. And we estimate that using Hansel type argument, reducing the problem to linear exponential sums. Okay, that would be also quite interesting work to go through because it connects with this workshop. But I thought I will focus on that other topic because an interesting problem emerges from that. Okay, that's all. Thank you.
Yeah, thank you, Stephan, for the nice talk. We have a few minutes for questions.
Trying to work out how to ask this question in a vague enough way. Thank you very much for the nice talk. So can one use these ideas to give, one can also study small values of a quadratic form with real coefficients. One can also study small values of a quadratic form with real coefficients. And in some sense, that's an analog at infinity of this. In some sense, this is a p-adic version of that.
Yes.
Do you think one can use these ideas to get new results in that problem?
Interesting questions. I didn't try that. So rather, we started thinking about the other case when we have prime solutions. But yeah, definitely. Yeah, I think so. One may try. Yeah, good suggestion.
Thank you.
Yeah. Yeah.
Yeah, so apparently there's work of Bergen which does this according to Vinay.
Yeah, and the circle method. So he uses smooth. Yes. Yeah. So one may look at that work.
Yeah, I have a question.
Yeah.
So your results pertain, of course, to quadratic forms. Now, there can be up to 3 cross terms. So did you look at, say, a1 x1 squared plus a2 x2 squared plus x3 squared plus one of the 3 cross terms only?
Yeah, so you mean general forms?
I'm thinking of something that's in between general and diagonal. So I could just decide that I want to have only the x1, x2 cross terms.
Okay.
So the x3 variable would still be isolated.
So that's actually a good suggestion. I mean, so we tried, or actually, at least I thought about that just last week again. Moment. I thought about, can we actually generalize our method to general quadratic forms? So maybe one should not be so ambitious, but just keep one cross term first and say the other ones are 0. Yeah, that's a good suggestion. I will think about that. Yeah, good.
Okay, very good. We do have time for another question, I would say. Or if not, then let's thank Stephan again.